Alright, guys, let's continue with our chapter 4 tutorials. Okay, we've done a lot. We've done a lot of things. We've seen the variable. We've done everything on DC drives. We've done everything on DC drives. First thing we look at is the AC drive, right? And under the AC motors, we have what? We have three-phase induction motors. Three-phase induction motors. And then we have the synchronous motors. Okay, so we have it like this. All right, but usually we don't use the synchronous motors. They are used for special purposes. So we're dealing with just the three-phase induction motors. So that's what we're working with. We're working with the three-phase induction motors. So the first thing we'll be looking at mainly is, let's look at the equivalent circuit for a three-phase induction motor. I have my magnetizing branch here, right? I have R1 here. I have X1. So this is my R1, X1. I have my X2 prime. So X2 prime is a stator reactance referred, right? Then I have my R2 prime over S here. So I have this. Then I have my voltage source supply there. So this is the equivalent circuit. So working with, I have my I2 prime flowing through here. All the formulas that we did. So go back to the videos and see the formulas when we spoke about the three-phase induction motors. All the formulas for finding TE, which is the torque, right? We know that torque is equal to what? 3 over omega S V1 squared over what? R1 R2 prime over S all squared plus XE squared multiplied by what? R2 prime over S. All these formulas, T max, remember T max formula, right? I think that was 3V1 squared over 2 omega S multiplying R1 square root of R1 squared XE squared. All these formulas work. Remember slip formula. Slip was what? R2 prime over square root of R1 squared plus XE squared. So all these formulas hold under this and in this part too. So we'll go through all the formulas. We've done them. Hello, yeah. So we've done all these formulas already in the previous video. So just go and refer to it, okay? Yeah. So we have this formula here. The T max formula. Here we do a plus and a minus. So the plus is for motoring, the minus is for generating. That's the next thing to note. Now, let's look at some approximations that we'll be working with. Okay. So you know this one refers to the old video. Now, let's see. See, I have the induction motor characteristics looking like this, right? The speed against torque. Looks like this, right? So this is my synchronous speed here, omega S. So from here, if this is my T max, this is my T max here, maximum torque. From this region to this region, it's called the large slip. It's a large slip. And from here to here, it's called small slip. Okay. So we can reduce the torque formula into a large slip approximation. And then also I can reduce this into a small slip approximation. So two approximations, small slip. So we know that the torque formula is what? E is equal to what? 3V1 squared over omega S multiplying what? R1 squared plus R1 plus R2 prime over S all squared plus XE squared times R2 prime over S. In the large slip approximation, all these values go away. All the resistances go away. So in the last approximation, I'll be left with torque is equal to 3V1 squared over omega S XE squared. 3V1 squared over omega squared XE squared times R2 prime times no times this. Yes. Times this. So this part goes away. So sorry, yeah, this part goes away, but this part still remains. So I'll still be left with R2 prime over S times R2 prime over S times R2 prime over S. So this is a large slip approximation. That's a large slip approximation. So in the large slip region, which is the starting region, this value is very small compared to this. So I'll be left with just this part of the equation. Then at starting, you know that at starting slip is 1. So when slip is 1, at starting, the starting torque, the slip becomes 1. So I just replace the slip with 1 here. That's the large slip. Now, for small slip approximation, the R1 and the X go away. So I'll just be left with the R2 prime over S in the equation. For small slip approximation, I'll just be left with this. This goes away. This goes away. I'll just be left with this. So again, torque is equal to 3v1 squared over omega s times R2 prime over S, right, squared times R2 prime over S. So this will take away one of the squares out. So I'm left with the torque being equal to 3v1 squared over omega s R2 prime over S can come and multiply here times S. So this is the torque for small slip approximation. This is the torque for small slip approximation. So for small slip approximation, torque is equal to what? 3v1 squared times S over omega s times R2 prime times R2 prime. That's it. So I can write a certain relation since this is directly related to V1 and S, right? It means that if I want to find a new value, say new torque over old torque, will be equal to all the direct proportionals will be at the top. So it's equal to what? V1 new squared. V1 new squared over what? V1 old squared times S new over S old times, so this needs to cancel each other, times what? Since this one is at the bottom, it will reverse. So it will become times R2 prime old over R2 prime new. So I need this relation to find any, so we'll see when we use something like this here. Maybe they'll give us something and we'll have to make something the subject here to find a new value. So we'll work around this one to get new values. Okay. So that's it for the large slip and the small slip approximation. Now, there are 6 ways in which the speed of induction motors can be controlled. 6 ways of varying or controlling speed of induction motors. The first one is varying the voltage. Second one is varying the rotor resistance. Third has to do with varying the frequency. Fourth, will vary both voltage and frequency. 5, they have something called the slip power recovery. Using the slip power recovery method. Then 6, we have by changing the number of poles. Changing the number of poles. So we'll take them one by one. So first, let's take varying the speed of induction motors by reducing the voltage. First, let's take by reducing the voltage or varying the voltage to control. Varying the voltage to control the speed of induction motors. Variation of that type. So controlling speed by varying motor terminal voltage. Controlling speed by varying the motor terminal voltage. Now, just like in DC motors, here, when you reduce the voltage, the speed reduces. When you reduce the voltage, the speed reduces. So I can make a characteristics looking like this here, right? Let's say this is V1. This is for V1. Now, when I reduce it from V1 to, let's say, somewhere around V1 over root, let me call this one, like I've reduced it by a factor of root 2. So let's say V1 over root 2. The characteristics look like this. So let me go to the slides. This is how it looks like. This graph here, this one here represents V1. This one here represents V1. This one represents V1 here. V1. This one is V1 over root 2. So you can see that here it has relatively lower speed. Relatively lower speed, right? Let me see. For the same torque here, you can see that this one has a higher speed than this. So reducing the voltage reduces the speed. Reducing the voltage reduces the speed. Now, you can see that over here, right, this is the maximum torque. So the stable region is this region here. So you can see that it has a small stable region. But then if I use a very large resistance rotor motor, I can have an characteristic like this here. And that will have what? That will have a very large stable region. Large stable region. Okay. So that's what this one I'm just showing us that if I use a high rotor resistance motor, I have a large stable region. So it will be explained, here that two pairs are obtained. It's not blah blah something. If special high rotor resistors are used, reasonably wide range speed range is obtained. Reasonably wide speed range is obtained. Now, a very important relation to know before we move on is this. Let me show you something here. And this is very important. We'll use it in a number of the questions. Okay. So note this ratio. PR is to PJR is to PM. 1 is to slip is to 1 minus slip. Note this relation very well. If I give you PJR and I say find PR, you use this part. You cross multiply and say, okay, SPR is equal to PJR. So PR will be what? PJR over S. If I give you PM and I say find PR, I'll use this side here. So I'll say, okay, PR times 1 minus slip is equal to PM. This relation is used like that. It's ratio. So with the one I've been given and the one I want, I'll just compare them and I'll cross multiply. And I'll use it to find what I want. Okay, so know this equation very well. Know this relation very, very well. Very, very, very well. Okay. So that's what he used to get this efficiency here. So PM over PR. Let's see. PM and PR. PM and PR. So as you can see, yes. So PM over PR, divide both sides by PR here over PR. PM over PR is equal to what? 1 minus slip. As you can see here. And this efficiency is PM over PR. And that is 1 minus slip. So at very, very high slips, the efficiency reduces because this will give me like, say 1 minus 8. 1 minus 0.8 is 0.2. 1 minus 0.2. So if the slip becomes very high, the efficiency will also reduce correspondingly. Okay. So that's it here. Okay. So as I said, we are looking at controlling the speed by varying the voltage, right? The stator voltage. Means that when you reduce the voltage, the speed reduces. Now let's see ways by which this can be done. Let's look at the conventional method, we'll look at the solid state method. Okay. Conventional method here, which is the old method, involves they can use variable three-phase auto transformers. Or just to vary the voltage, right? I can vary the output voltage of the auto transformer. And once I can vary that voltage, I can control the voltage and hence control the speed. They can also use variable resistors connected in series with the stator to cause voltage drops. So as I'm causing the voltage drops, I can control the voltage that gets to the stator and hence control the speed of the motor. So take the time and read all this part. We also have the solid state control method that makes use of the full wave AC voltage regulators. So read all this part. So this is how it looks like. This is how the full wave. This is how the AC regulator looks like. We connect them back to back to back, connected to the motor. We reduce the power factor and everything. So that's it. So let's take this question here. Question says that a three-phase star connected 180 volts. Kindly hold on. Okay, let's look at this question. So we have a three-phase star connected 180 volts. We have all everything we need. The first question says that calculate the motor speed at full voltage. Motor speed at full voltage. We know that was NR is equal to what? NS into bracket 1 minus slip. To find my speed, I need to find synchronous speed and the slip. So I can find my synchronous speed as was 60 F over P. NS is 60. I think the F was 60 over pole pair. Pole pair, they give me the number of poles to be 6, so the pole pair is 3 over 3. That's what 1200 rev per minute. 1200 rev per minute. That's this one. Let me also find my slip. Now I have the NS. I have to find my slip, right? Okay. Let's see. Say use small slip approximation. So let's find the formula for small slip approximation. Now for small slip approximation, the torque is equal to 3v1 squared s over omega s r2 prime. So over here, I have my torque, I have my v1, I found my synchronous speed, so I have my omega s here. So I can find my slip from here. So slip will be equal to torque times omega s times r2 prime over 3v1 squared over 3v1 squared. So that's how I can find my slip. That's how I can find my slip here. Yeah, so that's it here. So just you change the synchronous speed to rad per second, and you can use it inside the formula. And once I have my slip, I can find my NR. NS1 minus slip. That give me 1161 rev per minute. 1161 rev per minute. So that's it. That's how you find your speed. So this formula is very, very important. And what is a small slip approximation? I'll use this formula to find my slip and find my synchronous speed like this, and I put everything inside. So you get your slip here, and you put it here to find your speed. Then the B part says what? The B part says that repeat the same calculation if the voltage is reduced by 20%. So voltage is reduced by what? 20. So it means that my new voltage is what? 0.8 of the old voltage. The new voltage becomes 0.8 of the old voltage, right? Yes. So we mustn't solve. Let's go to the let's go to the slip formula, right? The slip formula is equal to what? Is equal to 3v1 squared slip over what? Over omega s r2 prime, right? So here, let me find a relationship between v1 and slip so that I can find a new, because varying the voltage causes the slip to change. So if I find a new slip, I can go ahead and use my NR is equal to NS1 minus slip. So I have to find the new slip at the new voltage. You can see that was, if everything is 1, if everything here is 1, 1, 1, 1, right? I can say that this and this here, the relation between them is what? V1 squared will be equal to 1 over S, right? So let me remind you. I can write that V1 squared S1, that's first slip, it must be equal to V2 squared times slip 2. So my slip 2 will be equal to what? V1 over V2 all squared times slip 1. So slip 2 V1 is V1. They say V2 is what? 0.8 of V1. I'll square this. Multiply by slip 1. Multiply by slip 1. Slip 1 in the question gave me what? That's the old slip, 0.037. So you put it inside here and you get 0.051. And once I have my new slip here, I can compute my new NR. Because varying the voltage causes the speed to change. Varying the voltage causes the slip to change, which will cause the speed to change. So that's it. That's how the procedure goes. That's how the procedure goes. Okay. So that's how you vary the speed by varying the voltage. That's how you vary the speed by varying the voltage. Okay, the next thing is controlling speed by varying the rotor resistance. Controlling speed by varying the rotor resistance. So if you vary the rotor resistance, what will happen? It will have an effect on the slip. We know that slip is equal to what? R2 prime over square root of what? R2 prime square root of R1 squared plus SE squared. So you can see that R2 prime, right? You can see that as I vary the rotor resistance here, it has an effect on the slip. And once it has an effect on the slip, it will subsequently have an effect on the speed. Consider that speed is what? Speed is ns into bracket 1 minus slip. Okay, so that's it. That's how that one works. So here, you add a resistance to the circuit. So there are two ways. There's a conventional method when you just add a variable three-phase resistance to the stator, then you vary it. And there is also a solid state control method that makes use of the of circuits. So look at all of them. Okay, so here, yes, as I said, you add the resistor. You can read all this part, okay? Okay, this are all the reading part. So this is how the characteristics looks like. The let's talk against speed. Let's see how it looks like. Talk against speed, right? Talk against speed. So this is my T max. They have the same T max. They have the same T max here. Here it goes here. This one still goes here, comes to meet here, and so on and so forth. So it looks something like this. So that's the characteristics as you can see from here. So here let me see. R4 is the biggest, right? R4 is the biggest. R4 is the biggest. That means that at a certain specific torque, increasing the rotor resistance reduces the speed. So the higher the resistance, the smaller the speed, as you can see here. Higher the resistance, the smaller the speed, because it increases the slip. It increases the slip. So that's it. When you increase the resistance, the slip also goes up. And when the slip goes up, the speed reduces because NR is equal to NS 1 minus slip. When slip goes up, this difference becomes small, hence NR comes down. So this is the characteristics. This is how it works. This is how it works here. Okay, so just read all this part here. Conventionally, you use external variable resistors, right, are connected to the rotor circuit. So that once you can vary the resistance, you can vary the slip. In solid state, this is what is used. So look at the solid state control. Let's look at the solid state control. The solid state control, in the solid state control, you have your motor here, right? This is my motor. So what you do is that you connect it to a bridge, a controller here, right? And then you pass it through an inductor. Then you connect it to a chopper circuit. You connect it to a chopper circuit, right? So you have something like this here. Then you control the resistance here. You have the resistance here, sorry, R naught. So this resistance is connected to the rotor of the motor. So by varying this resistance here, this R naught here, by varying the duty cycle of this here, I can vary the R naught, and this R naught is connected to the rotor. So I'm varying the resistance of the rotor, and because I'm varying the resistance of the rotor, I can vary the slip. And once I can vary the slip, I can vary the speed. So that's how the process goes. So let's see how this works. Now, this is the chopper, right? The chopper here. This is my chopper circuit here. Okay, so let's see. Now, what you can see here is that what you can make here out from this side is that the output voltage of this fully controlled three-phase, let me call it V naught. So for the three-phase fully controlled rectifier, V naught is what? Is 3 root 2 V over pi, right? Yes, 3 root 2 V over pi. 3 root 2 V. So I don't think it's fired. It's not fired, so there's no cos alpha. So let me clean it. So it's like this. Yeah. So V naught is equal to this. It's 3 root 2 V over pi. Now this V here, right? This V here is the rotor. This V here is the rotor voltage. This V here becomes the EMF of the rotor. Okay. So this formula implies I get V naught is equal to 3 root 2 times ER. But since you are dealing with in three phase, it becomes times root 3 of ER over pi. This is the rotor EMF. Then now root 2 times root 3 is root 6. So 3 root 6 over pi times ER. Right? Now when I refer ER, so now we are working at its root side. ER is for the primary. Right? So when I refer to root side, it's always for the stator side. When I refer to root side or secondary side, I'll have my V naught to be equal to 3 root 6 over pi. ER is SEOC. ER is SEOC. ER becomes SEOC times what? AM. Where AM is the turns ratio of the stator over the turns ratio of the rotor. So we have it like this here. No, let me go through that part again. I'm coming. Hold on. Let me go through the last part again. Let me go to the last part again. I said that V naught is equal to what? 3 root 2 over pi what? Root 3 ER, right? Times root 3 ER. And we said that, but ER is equal to what? S EOC. So ER is equal to S EOC, right? ER is S EOC. So now I want to refer this from the primary to the secondary side. So referring from primary to secondary side, you multiply this by the turns ratio, AM. That means I'll get my V naught to be equal to 3 root 2 over pi. This time is to give me root 6, so 3 root 6 over pi. Then my ER is now S EOC AM. Are you following me? EOC open circuit is the same as the supply voltage. So now I'll come and get 3 root 6 over pi S AM times supply voltage. So this is the formula here. This is the output voltage of the bridge controller here, the bridge rectifier here. So that's what you can see here. That's what you can see. So the steps start from here, right? ER is SEOC, the turns ratio multiplied by it. Then I have it like this here. So you must know this formula. You must know this formula of it. You must know that formula of it. Okay. Now that's V naught. But also I have a chopper circuit here, right? I have a chopper circuit here. Pay attention. I have a chopper circuit here. Now, if this chopper circuit is controlled by a switch as this, during the on state, what happens? This chopper will cause the current to flow through here. So it short circuits the output. But during the off state, the chopper supplies through it. It means that this chopper here, the output voltage recorded at the off state. Therefore, my V naught is 1 minus delta, that's the off state, times Vs. So this is the formula you must know. So V naught is here. And since they are parallel, it means this V naught and this V naught are the same. So I can write that 3 root 6 over pi S AMVS is equal to 1 minus delta times Vs. 1 minus delta times Vs. 1 minus delta times Vs. Okay. So yes. And that voltage is IDR naught. IDR naught. The voltage here will be the current. This current is ID. So ID comes here. I have ID times R naught. So let me clean this. Let me clean this part here. V naught is equal to ID R naught multiplied by 1 minus delta. So this V naught here. That's our V naught as we have there. Okay. Sure. The final formula that we must know. The final formula we must know is that I'm cleaning this, okay. The final formula we must know is that now the power that gets to this R naught, see when I do it, I put some R naught here, right? R naught. I had my chopper here, I had my inductance here. The power that gets to the R naught is called the slip power. It's given by PJR, slip power. The rotor slip power or PJR. PJR is equal to what? V naught ID. P is VI. Equal to the V naught times ID. V naught times ID. That's my PJR. V naught. And I found V naught to be this. So it just becomes this multiplied by ID. So this is another formula. So this part is more about knowing the formulas. Once you know the formulas, you'll be able to work around them. Once you know the formulas, you should be able to work around them. Okay. 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 So we've seen all the formulas that we'll be using, right? The formulas we'll be working with. So we can get into a question very soon. Let's see. So we said PJR is equal to V naught ID. PJR is equal to V naught ID. Now I know that for a motor, right? I know that for a motor, PR PR is what? Torque times synchronous speed. PR is torque times synchronous speed, right? And I know that from the formula 1 is to S is to 1 minus S, I have PR, PJR is to PM. From here, PR times slip. So SPR is equal to torque times omega S. So from here, sorry, SPR is equal to what? SPR is equal to PJR, right? SPR is equal to PJR. Okay. Over here, I can say that I want to make something that's happening. Let me show you. So PR is PJR over S. PR is PJR over S, right? PR is PJR over S. So it means if I divide PJR by S here, you see, at first in PJR there was an S here. So if I divide this by slip, I'll get PR. That's all we are trying to say in this formula here. Okay. And this question in our next. I hope you understand. So I'll just solve this question in our next video. All right. Thank you very much.